Okay, welcome back. This is Linear Algebra Week 12, Monday, 1st November 2021. So in today's lecture, I would go through examples of how to calculate eigenvalues and eigenvectors from given A. So basically, we'll just go through the mechanics of generating the characteristic equations to solve for the eigenvalue. And that once we have the eigenvalue, then we will put it here in the characteristic equation with x here to solve for non-trivial x. The word non-trivial by now, you understand that it means non-zero. So we're not interested in eigenvectors that are zero. There's no such thing. We need a non-zero x for this equation to hold. And when this equation holds, then it is an eigenvector associated with the corresponding eigenvalue that we have calculated, lambda. The lecture notes are in 8.1 and 8.12. And I would ask you to go to your lecture notes here, where I release a support. So in chapter 8, I released tutorial 8 support, tutorial 7 support, tutorial 6 support, and in this, there are additional slides for you for your reference. So now let's take a look at these slides. And in these slides, basically I collected many YouTube videos along the way to help you with your tutorial 8. So these are it. For example, I have a whole page of how to calculate the eigenvalues and eigenvectors from everybody else. So depending on your interest, you can watch any of these videos. They are all talking about the same thing. Nothing has changed for the last 50 years for eigenvalue and eigenvectors. And so you can look at any of these, and then as long as you figure them out, that'll be fine. So for our purpose, what do we need you to do, at least for our exam, is that you need to calculate 2 by 2, the eigenvalue and eigenvectors, up to 3 by 3. We are never going to do more than that unless there are special matrices. So when we special matrices, meaning that maybe they are already singular, they are upper triangle or lower triangle. So some of these matrices have very special structure, and therefore their singular values and their eigenvalues are also obvious. Okay, but for exam purposes, if we ever need you to calculate by brute force, then you only need to calculate up to 3 by 3. As well as special matrices, you'll see that in tutorial 8, question number 3, where we have a singular matrix, and then we are asking you to find the eigenvalue and eigenvectors of it. So in today's lecture, what we are going to do is we are going to do a very simple 2 by 2, and let's see how we go. All right. Now let's begin. So let's recap. The definition of eigenvalue and eigenvector is, first we are given A, and A must be square, and we are multiplying by a vector. So let's call this n by n matrix, and n must be Rn. So let's restrict ourselves to a real vector first, and you realize that actually we can go into complex vectors as well. And then lambda is a scalar, real first, and then x. All right, so it can be complex, guys. Complex is possible. Now, so you must understand what it means is that A transform X to a scaled version of itself. So basically, the scaled version is simply scaled. How scaled? The lambda scale itself is X. So the word Argon means itself in German. So what A did to X was that it either stretches it if lambda is greater than 1 or make it smaller. Or in fact, it can flip it around if lambda is negative. But X still points in that same direction. And there are many interesting things that is useful if we can find such an X. But to find such an X, it is not trivial unless A has some interesting structure. So you realize that I've just given you a problem that you need to solve for two unknowns. What is lambda and what is X? And how many lambdas are there and how many X's are there? So in the n by n case, the maximum number of lambda is lambda 1 to lambda n. And the number of X, let's call this P1 to Pn, okay? So typically, for every eigenvalue, you would find the corresponding eigenvector. And later on, you can have other things like repeated eigenvalues, meaning that lambda 1 is the same as lambda 2. And for some degenerated case, you cannot find the corresponding eigenvectors. Okay, so you need to figure out all this in the exam. Now, for 2 by 2, therefore for 2 by 2, the maximum we'll get is lambda 1 and lambda 2, and associated with it P1 and P2. P1 and P2 means the eigenvectors of, so here the 1 here is talking about this 1 here. So P1 is associated with lambda 1. P2 is associated with lambda 2. Right. Okay. So let's proceed from this equation 1 here. And then now we go to equation 2 here. So remember, on the left-hand side is a matrix multiplying by a vector. On the right-hand side, unfortunately, is a scalar multiplying by a vector. So we can't merge them. But we now know that, well, all we need to do is to multiply the scalar by a matrix. So we'll get a matrix here. Remember, lambda is a scalar. For example, lambda is 2, and now A is a 2 by 2 matrix, so lambda is 3. Let's try. And lambda times I is a 3003. What we are trying to get is the identity multiplying by the lambda for lambda equals to 3. That's all. So here, then you say, I've just changed a scalar to a matrix. So didn't I change something? Well, nothing changes because this is still an X. So lambda times I times X is the same as lambda X. So brute force, you can go and see it for yourself. Now, once we are in this equation, then the left-hand side is matrix multiplied by vector. Right-hand side is matrix multiplied by vector. The common denominator is the common factor is X. So we can move it together. And then we can collapse it. Right. And then now here's the interesting thing. We want lambda, we want X. So we have two problems to solve, lambda and X. And it appears that you can't solve this, right? You're only given A. So there's so many things moving around. But we want X that is non-zero. So this is the critical part. A non-zero X basically means that this guy cannot be the zero vector. Of course, if I want to, all these zero are not the scalar zero, they are the zero vector belonging to Rn. No. Now, please remember, this guy is a matrix. A minus lambda I is a matrix. A matrix multiplying by a vector that will produce a zero vector. When X is not a zero vector, this matrix is very special. It is singular. It has dependent column. So where did I get this all this information? Dependent column. Where did I get all this information from? The invertible matrix theorem. Not only that, if it is singular, if it has dependent column, the determinant of this matrix is equals to 0. So among all the invertible matrix theorem, we are going to use this fact. So we are going to say that since we want this equation to be true and X to be a non-zero, then this matrix A minus lambda X must be singular and its determinant must be 0. Therefore, the determinant of A minus lambda I must be 0. Now, let's try to let's have a general A first. Okay, let A be equals to A, B, C, D, and then lambda I equals to lambda 0, 0, lambda. So remember, we are only working, our example is a 2 by 2A, okay? And therefore, A minus lambda I is A, B, C, D minus lambda 0, 0, lambda. And then the determinant of, so this is a special part, all right? D minus lambda. So basically, we have ended up here to reach this point. And you know how to, and ABCs and lambdas are nothing but real numbers in this case. And we know how to solve for a 2 by 2. So the determinant of a 2 by 2 is simply this guy on the top left multiplied by the bottom right minus CD. So it's A minus lambda, D minus lambda minus CB. Okay. All right. So once you have figured this out, then we're going to get the equation, which is AD minus lambda D minus A lambda plus lambda square minus CB. Let's collect it out together. So it's lambda square and then minus lambda D minus A lambda plus AD minus CB. All right, so this is the first, this is the equation without lambda. This is only with one lambda, and this is with the lambda squared. And you know that this is a quadratic equation, and therefore you can factor it out to the roots of the equation. So you're going to solve for the roots of the equation. Right, and then you get some values here. So we are just solving for this simple quadratic equation, and you know that any quadratic equations of this form can be solved by our, let's try. Okay, I'm going to simplify for you first. Lambda square minus A plus D lambda plus AD minus CB. So equations of this form, remember, let's have an equation. Just recap, okay, guys? So recap. We have an equation that is ax squared plus bx plus c equals to 0. So this is your A level or O level problem. And what are the x's that makes the equation 0 is x equals to minus b plus minus square root of b squared minus 4ac over 2a. So in this particular case, there are three cases. The first case is that b squared minus 4ac, I should say this term here is positive. If it is positive, then we have two, two real roots. Second case is this term is equals to 0. Then we have only one real root. And the third case is less than 0. Then we have complex roots, complex conjugate roots. So these are the three cases to solve for the x, or in our case, of course, it was to solve for our lambda. Okay, so please refer to this, and then you guys can figure it out. So we have now find our lambda. All right, and then with that, then we can proceed. Now, so to be concrete, I'm going to give you an example. All right, and then we'll go through it. So this is still the theory part. So now let's have a concrete example. All right, page number 3 now. Okay, so I'm going to give you a simple A, which is a 2 by 2. 2, 0, minus 1, 1. And let's say the question asks, find all the eigenvalue and their corresponding eigenvectors. So we are just going to do this. We'll start with this immediate equation. Ax equals to lambda x, and I'll jump now to A minus lambda I x equals to 0, and then we are going to figure out that we need to find the determinant of A, which is 2, 0, minus 1, 1, minus, then we have lambda, 0, 0, lambda, and then we are going to find the determinant, which sometimes is shown by this solid line across, 2 minus lambda minus 1. So don't get the notations wrong, please. And then this is 1 minus lambda. And then the determinant is 2 minus lambda, 1 minus lambda, and the other guy is minus 1 times 0, and therefore implying that lambda is equals to 2 and lambda equals to 1. Okay, so in this simple case, this is what I tell you is a trick. Every time I give you the upper triangle or lower triangle matrix, the eigenvalue shows itself in the diagonal 2 and 1. So there's nothing, in fact, for me to do. Okay, but by brute force, you can see that it's the same. Eigenvalue is 2 and the eigenvalue is 1. So that's the first step. The second step is, so for each eigenvalue, we're now going to solve. So let's go and try lambda equals to 2 first. For example, lambda equals to 2 first. Let's solve. Let's find P1. Let's find P. associated with lambda equals to 2. Okay. Now, so what do? So remember, we'll start with that equation here. A minus lambda I x equals to 0, lambda equals to 2. So I'm going to substitute 2 into 2 minus 1, 0, 1. And I'm going to substitute 2 into this equation here. 2, 0, 0, 2. The whole thing multiplying by x equals to 0. Now, what does this reduce to? 2 minus 2 is 0. Minus 1, 0, minus 1. So this matrix here, multiplying by x is equals to 0 vector. So this is R2. This guy is R2. Now it's obvious that the columns are dependent. Therefore, all I need to do is to get the 0 vector, the x, okay, the x can be 1. The second column, the second entry must be 0. Or in fact, any alpha, right? Any alpha times the first column, as long as the second value is 0, this guy is 0, then it will be. So therefore, this vector is an eigenvector for what? For lambda equals to 2. Okay. So how do I know? I mean, then you say that for sanity check, right? A lambda 0 equals to, so we are going to just put everything 0 minus 1, 1, lambda 0. What do I get? So I get did I make a mistake? No. Let me find. Okay. So it's 2 is 2 lambda. Sorry. Yeah, I didn't make a mistake, of course. Because why? This is A, this is X, this is 2x. Okay, because this is 2. All right, yeah, that's why. Okay, so this is X, this is lambda. So you see that, okay, I have given you a matrix, and then now I figure out that any vectors lambda 0 is an eigenvector, and 2 is the eigenvalue. All right, let's find the other one, okay? What about the other one? Okay. So now I have C. Let's find eigenvector for lambda equals 2 in our case. The second one is 1. Again, 2 minus 1. Oops. 0, 1. And then lambda equals to 1 basically means the identity. And then we have x equals to 0. And now we continue. And 2 minus 1 is 1. Minus 1. 0. 1 minus 1 is 0. Again, the first column and the second column are dependent because the second column is nothing but the first column multiplied by minus 1. So this matrix is singular, and therefore we can have a non-trivial solution. So guys, you remember how to find the parametric solutions for this homogeneous equation. So these are homogeneous equation, right? Something equals to 0. The solution of this is the solution that we want, x. All right, so in this case, let's This is the typical problem that you face. I mean, you can think of X as X1 and X2. So actually you're doing this. X1 and X2 equals to 0. Remember that X is R2, right? And therefore now I just show it to you as a column vector. And now we are doing implying X1 minus X2 equals to 0. And remember that this guy is the pivot, and therefore he is fixed. Therefore, what we have is X1 equals to X2. And then, so X2 is free, right? This is the free variable, right? And then because he doesn't have a pivot, so therefore, X is equals to X1, X2, and since X2 is free, so we can do it this way. So this is the solution we want. This is the eigenvector. And in fact, equals to any alpha. Okay, again, any alpha is an eigenvector. So remember, it's not 1, 1 is the eigenvector. Any vector that points in the direction 1, 1 is an eigenvector. All right, let's what do you call it? Verify that this is true. Let's verify. Sanity check. So we have 2, 0, minus 1, 1, and then I'm going to multiply by 1, 1. What do I get? I get 2 minus 1 is 1, 0, 1 is 1. So I get Ax equals to x. So now I try to change it to alpha. So this again is 2 times alpha minus alpha is alpha on the top, 0. So this is also alpha. So that's true. So therefore I verify that lambda equals to 1 is an eigenvalue, and x being lambda lambda is an eigenvector. Now in MATLAB, they will always give you an eigenvector that is normalized. So for MATLAB, okay, eigenvector has been normalized to unit length. Okay, so this is what we need you to do in the exams, at least for eigenvalues and eigenvectors. Okay, I'll pause now and take questions. Right. Student asks, what is the applications of eigenvalues and eigenvectors in our course? At least, this is the most important application. AK, a to the power of k, where a is the square matrix and k is a very big number, like 1,000. So a times a times a 1,000 times is very difficult to compute if a does not have a what do you call it, a nice structure. But if A has a nice structure, or in this case D, where D is a diagonal matrix, then D by D is simply D by D, and because it's diagonal, so many zeros are around, only the diagonals are being square in D square, and D by D cube, again the diagonals are square. So it is obvious that dk is the diagonal value square, diagonal value k power. So if we can reduce a matrix to a diagonal, then something useful happens. So the eigenvalue and eigenvectors actually reduces a matrix A to a diagonal matrix. So we call eigenvalue decomposition diagonalization as well. Right, let's see where's the diagonalization. A is this 2 by 2 matrix. You now can find the eigenvector and the eigenvalue. The eigenvalue is 5 and 3. Then you can find the corresponding eigenvector. 1 and minus 1 is the eigenvector for 5. 1 and minus 2 is the eigenvector for 3. So the order matters. Okay. This is D11 corresponding to column 1. This is D22 corresponding to this guy. So where is A? All right. A is P times D times P inverse. Go and multiply P times D times inverse of this guy. You'll get A. Okay. So this process is called diagonalization. If you can find a complete n basis, eigenbasis, n number of independent eigenvectors, then you can diagonalize the matrix. So what's so cool about this? Look at A square. A square is PDP minus 1 because that's what we are given, and we found PD, and then of course P minus 1 is trivial. But if this is A and this is A, P minus 1 times P is I, because hey, they're gone. And now we have D times D. D times D is trivial because D square is trivial because D is a diagonal matrix. So D square is nothing but the diagonal element square. So we have a P here, we have a D square here, and we have a P minus 1 for A square. Now imagine AK. So all we are doing is we are performing the K multiplication on the diagonal matrix. Of course, we have this overhead to do P minus 1 here and to do P here, but this is very cheap compared to trying to multiply A times A times A. Okay, do I answer your question? Yes. All right. So you have to figure this out, and then yep. So this is just a few examples. In previous quizzes, we did ask you to find a to the power of 100 times x. So if you don't know how to do this, you'll never be able to compute 800 times. So you have to compute this form and then multiply by x. So then it's very, very cheap. Right? Okay, so that's diagonalization here. All right, I think that is in tutorial 8, one of the later questions you have to figure out. You definitely in past quizzes we did ask compute a to the power of 100. All right, and then you have to. In fact, we ask you to compute a to the power of 100 multiplying by a vector x. Then we give you an x. You will need to find P and D. So what is P and D? P is the columns of P are the eigenvectors, and the diagonal entries are the eigenvalue. So we have just done a 2 by 2 gun. Okay, so if I so you take this A, and now you find the eigenvalue and the eigenvector. Like what I've done, you will find this 5 and 3, and once you have solved for 5 and 3, you substitute in to find P1 and P2. Now, if you do it in MATLAB, you will not get 1 and minus 1. You'll get a normalized version of this and a normalized version of this. Okay, so I'll try to start MATLAB next week. All right. So in today's lecture, all I did was, so let me refresh now. So in today's lecture, all I did was to show you a concrete example of a 2x2 matrix Argon decomposition. And then first I give you the theory of it, and then I give you a concrete example. So this is the concrete example. I'm going to now copy out the values so that you guys can see. Okay, so what I did was I say that A is equals to 2, 0, minus 1, 1. Find lambda and corresponding eigenvector. And we found lambda equals to 2 and 1, right? And then the eigenvalue, we found it to be for 2. For 2, what is the value? For 2, it is 1, 0. For lambda equals to 2. And the other guy is, for lambda equals to 1, it is 1, 1. So the matrix, so this is lambda equals to 1. So P is equals to 1, 0 for the first column. So let's see. And then the other guy is 1, 1. What about D? D, this is 2, 0, 0, 1. Okay. And therefore, A is equals to 1, 0, 1, 1. This is P. This is D. Please remember, okay, guys, don't write it wrong. If this is lambda 1, this guy is P1. If this is lambda 2, this guy is, sorry, this whole guy is P2. Okay, that's the idea. So the column position and everything counts. Then the last one, right? Because I'm lazy, I will write it this way, but I wrote it as P minus 1. So this is P, this is D, and this is P minus 1 is equals to A. All right, so you can verify and you just multiply this matrix by this diagonal matrix by its inverse, and you should get exactly what is this matrix, right? Will the number of eigenvectors and eigenvalues always be the same? No. You will be able to get the roots of the equation of the polynomial up to n order. So the number of eigenvalues would be n, but the number of eigenvectors may not be n. And therefore, when it is not n, then the columns of P is not complete. You don't have n of them, and therefore inverse does not exist. And therefore, the matrix is not diagonalizable. Okay, where did I say this? I think it is maybe here in 8.1.3. Yeah, here. Okay, please read. Some matrices are not diagonalizable. All right. Okay, yeah, all is here. Do I have a prompt? Yep, so you read all this. Yeah, it's quite involved. It's talking about here, algebraic multiplicity and geometric multiplicity. The number of eigenvalues can be up to n, but the number of eigenvectors may not be up to n. When that happens, then we do not have a invertible P. All right. Okay, I think I'll stop now. I'll pause the recording. So in next week, on Friday, I will continue with more examples, and then I would also complete my recordings of the tutorials, and then you guys can see. All right.